Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our third lecture covering material from Chapter 3. Disclaimer: this is in no way equivalent to our actual lecture where we discuss and practice the material in much more detail. We begin this lecture with percent composition. This is the mass of each element as a percent of the total mass of the compound. The formula used is the mass of the element divided by the total mass of the compound times 100. We use molar masses from the periodic table. To calculate the percent composition of hydrogen, we will take the mass from the periodic table, which is 1.008 times 2, since there are 2 atoms of hydrogen, divided by the mass of the entire formula, 2 hydrogens plus the mass of oxygen. We can subtract this result from 100 to get the percent oxygen, or solve as the same as we did for hydrogen. We talked about empirical formulas previously. We can define an empirical formula as the simplest positive integer ratio of atoms present in a compound. To determine a formula, we need to know if the ratio of atoms in the compound. This is also the mole-mole ratio of those atoms because mole is simply a count. To determine moles of each element, we need to start with a mass. So the first step in this problem is to define the total mass of our sample. We can use any value, but if we assume the sample is 100 grams, then our percent values correspond to grams of each. Next, we can convert to moles. Since we need a whole number ratio, we divide all by the smallest number of moles. An example of converting to moles for K is shown. If we divide all by 0.6319, our whole number mole ratio is 213 for the empirical formula K2SO3. Pause the video and try this one on your own. The answer is NH2. We can determine the molecular formula from the empirical formula as long as the molar mass of the molecular formula is given. We divide the molar mass by the mass of the empirical formula to get a multiplier. Multiply each element in the empirical formula by this to get the molecular formula. Give this a try. The answer is N2H4. We can use the term salt for any ionic compound. Recall that ionic compounds form a crystal lattice or a three-dimensional repeating structure, and when this happens, water molecules may become trapped within the crystal. In this example, there are 6 water molecules for every 1 cobalt-2 chloride formula unit. This is another hydrate which has 2 water molecules for every 1 barium chloride. Realize there are many mole-mole ratios within this formula that we can use as factors. Examples are 1 barium chloride equals 2 water, or 1 barium equals 4 hydrogen. A common hydrate problem is to determine the number of water molecules present per unit of salt. This can be done easily in the laboratory without sophisticated equipment. The method is to heat the hydrated compound hot enough to vaporize the water, which releases it from the crystal lattice. In this example, we start with 1.023 grams of hydrated salt, and after heating, the mass is 0.654 grams. This is the mass of copper-2 sulfate with no water. We call this anhydrous copper-2 sulfate. The difference between the starting and finishing mass is the mass of the water. Using the steps shown, see if you can solve this on your own. The answer is 5 waters. This is named copper-2 sulfate pentahydrate. This is a very common exam question, so here is another practice problem with the answer provided. Make sure you can do these on your own before your first exam. Thanks for watching. Please give this video a thumbs up and subscribe if you would like to see more mini lectures from the Professor's DuBois channel.